Welcome everybody. Today I would like to present you our tool QFlow, which uses quantitative information flow to help the designer in designing a secure hardware. My name is Leonard and I would like to start with why we actually conducted this research. The high complexity of modern hardware designs and the many parties being involved lead to many design mistakes in the hardware description, which lead then to vulnerabilities. This means that even for a secure algorithm, they could suffer from insecure implementations. We will focus on the RTL design process and assume that the rest of the production flow is secured by other means, for example, logic locking. So we will focus on the property of confidentiality of sensitive signal. For a more concrete example, this might mean that we would like to protect our cryptographic keys or user data in trusted components from being leaked to untrusted components. How could we actually assist the designer in this process? We could use testing of the tip, but we would have to rely on the test coverage. Additionally, we could use formal verification, which is not suitable for inexperienced users. Additionally, there's information flow analysis. So what is actually information flow analysis? Information flow analysis utilizes the non-interference property, which means that if we mark components or signals in our hardware description as highly sensitive, as high, the observable outputs cannot rely or being interfered by from these highly sensitive data. For a more concrete example, this might mean that we have an observable output of a ciphertext, that it cannot depend on the encryption key, which is not suitable for an encryption engine. So what we could do in those cases is we could quantify how much information about the encryption key can actually be found in the ciphertext. For this purpose, we can use quantitative information flow. There is already work out there which name is Verilog, which uses quantitative information flow to quantify how much information from the key actually flows to the output ports of your top module. But we found some insecurities in the tool, that way we conducted our own research. For the threat model, the hardware designer is aware of the whole complete hardware design, is able to observing outputs at a random moment in time, but is not able to set any input values himself. So how does our tool actually work like? We have our Verilog description of our hardware, mark our highly sensitive data here as high, have the input probabilities of our inputs here and a list of untrusted components. Those information are passed. Verilog is passed by Verilog, which forms then a data flow graph, which is merged further, and the dependencies, the probabilities are computed for the different intermediate signals. Additionally, we compute the leakages using equations from quantitative information flow, compare those values with two thresholds to determine for every secret bit whether the leakage can be neglected or not. In that case, we have a leakage of 0.75 bit for the bit I1 here in that case, and also have the leakage path. For the evaluation, we started with evaluating 2 rounds of pipelined AES, as it's supposed to be sufficient to obfuscate a signal fully. And in that case, we got for every secret bit a leakage value. The lowest one we use now as a warning threshold for later on, and the average of all the other values we used as a detection threshold. Those thresholds can be seen here in our plots when we conducted our further evaluation on the Trojan-infested crypto accelerator from TrustHub. In the first case, you can see the AES T100 benchmark, where you can see that the Trojan leaks the first 8 bit completely, whereby you can see for the RSA benchmark that the complete exponent bit is leaked completely. The modulo additionally has 2 false positive detections by our tool. Furthermore, we implemented 3 additional Trojans, which still remain undetected by Verilog. In this example, you can see a Trojan which concatenates and deconcatenates a value over and over again until it's not recognized by Verilog any longer. Additionally, we focused our evaluation on the remaining benchmarks of the TrustHub, and as you can see, all leakages were detected and quantified by our tool, whereby you have the false positive detections here for the RSA benchmarks, and you can see the 3 benchmarks which were implemented by us remain undetected by Verilog, but were detected and quantified by our tool. To summarize and conclude my talk, I just presented you a tool QFlow, which uses a static quantitative analysis to determine information leakages in your hardware description. The tool is pretty user-friendly, works in a bitwise fashion to make the values understandable. No leakages in the benchmarks were overlooked. And for future work, we would like to reduce the number of false positives and broaden the spectrum of the attack scenario to allow the user to set input values himself. Thank you for your attention.